In 2022, a team of physicists reported that a 9-qubit quantum circuit had successfully passed quantum information through a holographic wormhole. The experiment took place on Google's Sycamore quantum processor, housed inside a dilution refrigerator cooled to within a fraction of degree of absolute zero. This was presented as a literal mathematical realization of gravity. Under the right mathematical lens, the team argued these superconducting circuits were identical to a black hole sitting in a higher dimensional space. The claim stood for over 2 years. Then, in February 2025, 3 physicists from UC Berkeley published a formal critique in the journal Nature that challenged the entire gravitational interpretation. The Berkeley group did not find a hardware error. The Sycamore qubits performed their logic gates as programmed. The issue was found in the theoretical framework used to bridge the gap between the circuit and the wormhole. This case study defines the verification problem. It demonstrates how a quantum simulation can produce perfectly accurate data that is nevertheless untethered from reality because the mathematical dictionary mapping the hardware to the physics is broken. Quantum simulation operates on a different logic than traditional modeling. In this regime, the physical hardware shares the same quantum rules as the target system, meaning the circuit's evolution acts as a direct physical realization of the underlying equations. This realization relies on the ADS-CFT correspondence. Worked out by Juan Maldacena in the late 1990s, it proves that specific quantum theories are mathematically interchangeable with theories of gravity in a curved space region. The 2022 claim carried significant weight because it originated from researchers at Caltech and Harvard, suggesting that the abstract math of holography could finally be tested in a controlled lab environment. To act as a dual to a black hole, a quantum system must saturate the chaos bound, scrambling information at the absolute maximum rate allowed by the laws of physics. Physicists use the SYK model to achieve this. It describes a collection of particles interacting in a maximally chaotic pattern, mirroring the thermalization properties of a black hole. If the circuit fails to meet this specific chaos bound, the mathematical link is severed. The experiment is no longer a study of gravity, it is simply a study of superconducting circuits. The full SYK model requires hundreds of Majorana fermions interacting in a random all-to-all network. Information dropped into this dense topology scatters instantly, uniformly tinting the global state. However, this complexity scales exponentially, rapidly outpacing the capacity of any current quantum hardware. Running the full model requires hundreds of fault-tolerant logical qubits, a technology that doesn't yet exist. To bridge this gap, the 2022 team used a machine learning algorithm to prune the model, stripping away interactions until it fit onto just 9 physical qubits. The algorithm was tasked with preserving the key signatures of holographic duality while removing as many interactions as possible. This sparsification disconnected the hardware from the target physics. By forcing the model to fit the limitations of a 9-qubit chip, the algorithm unknowingly removed the specific complexity required for gravitational behavior. The Berkeley team discovered that the stripped-down, machine-learned Hamiltonian was entirely commuting. In a commuting system, the order of operations doesn't matter. Without non-commuting interference, parts of the system evolved independently in parallel, never actually interacting. But genuine black hole physics requires the opposite, non-commuting chaos where information irreversibly scrambles. The Caltech team pointed to a pattern in the data called perfect size winding, which they argued was a specific fingerprint of gravitational teleportation. But the Berkeley group proved that perfect size winding is a generic feature of small commuting quantum systems. It appears for algebraic reasons that have nothing to do with black holes or wormholes. This is a version of the lamppost problem. By simplifying the system so it could be analyzed, the researchers created a scenario where the simplification itself produced the pattern they were looking for. The signature wasn't a signal from quantum gravity. It was a mathematical shadow cast by the machine learning algorithm's own pruning process. While the 9-qubit experiment was contested, a much larger simulation from 2025 provides a contrast in how results are verified. Researchers at the Jülich Supercomputing Center utilized over 5,000 qubits on a D-wave advantage system to model the end of the universe. They used a 1D icing model to simulate quantum tunneling and the formation of vacuum bubbles, the mechanism that would occur if our universe were sitting in a metastable false vacuum. This experiment was accepted because the Ising model is well characterized, offering a clean, verifiable line between theory and qubits. Unlike the holographic attempts, unproven machine learning shortcuts, this simulation operated in a regime confirmed by independent evidence. The disparity in these two experiments shows that high qubit counts mean very little if the theoretical bridge between the hardware and the physics is broken. This brings us to the core verification problem. Quantum computers are designed to solve problems that classical computers cannot. If a classical computer could check the result, we wouldn't need the quantum hardware in the first place. Historically, experimental physics relied on independent replication. If an accelerator detected a new particle, another lab built a similar detector to confirm it. This methodology fails for large quantum arrays. The complexity of the quantum state is so high that we cannot extract or examine it without destroying the information we are trying to verify. The field is shifting toward a reliance on rigorous mathematical physics to certify these simulations. We now need mathematical proof that a circuit is faithful to its target physics before the simulation even begins. Although the 2022 result was identified as an artifact, the goal of probing holographic gravity in a laboratory remains a central effort in modern physics. As quantum hardware continues to advance, the limiting factor in our understanding of the universe may no longer be the power of our computers, but the rigor of the mathematics we use to interpret them.